Here we have a situation where we start out with some mass of a liquid, in this case let's call it water, at some temperature, T1, and it's a piston above the liquid, and it's held in place by a stop, and there's vacuum above it. And what we're going to do is pull out the stop, let it go to equilibrium. So what's going to happen is some of the water is going to evaporate, and we'll call the mass that evaporates mass 2 vapor. So the mass of liquid would be the initial mass minus how much evaporates. The temperature is going to be different, and of course now we're going to have some pressure, whereas we started with no pressure above the piston. And so we'd like to determine how much evaporates and what is the temperature at equilibrium, and correspondingly what is the pressure. And so we can look at this system to help visualize what's happening. Let's say a small amount evaporates. Well, it needs to have energy to evaporate. That comes from cooling down everything, and most of that is the liquid, because there's going to be much more liquid than vapor volume. And so we have to cool down the system. We're assuming the heat capacity of the container is 0 to make the calculations easier. We're assuming it's adiabatic. And if a small amount evaporates, the temperature drops. The amount that evaporates, then we could determine the pressure from the volume, the amount evaporated, ideal gas law, molecular weight. And then we could check, does that correspond to vapor-liquid equilibrium? Is the pressure the saturation pressure? If not, let's look at a little more evaporates. We cool down a little more. Eventually we're going to be at equilibrium where the pressure is the saturation pressure and the temperature, of course, the saturation temperature. So the equations that we're going to use, we have to, one, and that's going to be the ideal gas law. That relates the volume of the container and the final pressure to the mass in the vapor phase, and we'll divide it by its molecular weight and the gas constant, the temperature. Well, we need to have vapor-liquid equilibrium, and vapor-liquid equilibrium assumes that we're at saturation pressure, so we need an equation, and we're going to just write down the Antoine equation because that makes it easiest to solve. That should be temperature T2, so T2 plus C, A, B, and C are all constants. And then the last equation we need is the energy balance. It's a closed system. The change in internal energy, the total, not per mole, but the total is going to be 0. And so we want to write down an equation that says the initial amount, so we only have liquid, so keep in mind this is per gram or kilogram, but per mass times the mass. That's how much the initial internal energy. The final is, well, we have liquid remaining, which is mass 1 minus how much evaporated. Internal energy of liquid, final. And then we have the mass that evaporated times internal energy of the vapor. So that's the energy balance for the system, and what we want to do is then substitute in, so we can write this in terms of heat capacities and delta U of vaporization. Now, remember we worked with internal energy, we're always looking at changes, and there's no absolute values, so we can pick a reference system. So for example, here's what we're going to do. We can say internal energy of a liquid at some temperature is the internal energy at the reference temperature plus the heat capacity of the liquid, temperature minus the reference temperature. Now keep in mind, for a liquid this is essentially the same as Cp. It's not true for a gas, but for a liquid. And we can make our life easy by saying our reference value is going to be 0 at T reference equal to T1, our starting temperature. Okay, so let's make this substitution then into our energy balance. So for the left side of the equation, I've changed it to Cp for the liquid. Temperature we start's T1. Our reference temperature is T1. So of course this is going to end up being 0 for the term on the left side. The right side, look at first the amount of liquid. So the amount of liquid, since we're going to use heat capacity for the liquid, T2 minus our reference temperature, T1. And now for the vapor, it's a little more complicated. There's the mass of the vapor. So we can look at this in different ways. What we're going to do is we could visualize the vapor. We could visualize the vapor evaporating at our reference temperature and then heating up that vapor to the final temperature. So at our reference temperature for liquid, the internal energy is 0. And then we have a change due to vaporization. And I'll use the notation at temperature T1. And then we have CV for the vapor, T2 minus T1, our reference temperature. Well, this is our energy balance. So remember, this is 0. So we have an equation where our unknowns, T2, mass of vapor, and then of course we have 3 equations, so P2. So we have 3 unknowns, and then the 3 equations are ideal gas law, Antoine's equation, and delta U total equals 0, which we've just written in terms of masses. So we have 3 equations that we can solve simultaneously to determine the final conditions, how much evaporates, and what's that final temperature.